All right, okay, back to it. So the switch was open for a long time before t equals 0. Then at t equals 0, the switch closes. Find Vx at 5 milliseconds. Vx is defined to be this voltage. And you can also just say that Vx is the voltage across this resistor, right? I don't know why they defined it like this, but at the end of the day, Vx is just the voltage difference across this node and that node, or the resistor, right? So something to keep in mind. And just like last problem, first thing we want to do is just choose a direction for our current. So I like to go down, so that's what I'm going to do. Define IL of t to be going down. Now, first step is to draw the circuit for t less than 0, which the switch is open at this point. And when we draw the circuit at this point, we can short this inductor because the problem tells us that the switch was open in this position for a quote-unquote long time. In other words, the inductor is in steady state condition. So this is the circuit we are working with. And this is our IL of 0, 6.3 kiloohms, 2.2 kiloohms, minus 12 volts. And I'm choosing not to draw everything to the right of the switch because it is disconnected from the circuit, right? The switch is open, so nothing on this right half of the circuit is going to impact the left half. So we're just going to get rid of it. Now, what is the value of IL of 0? Or what would the fraction be? Right?
Negative 12 volts over 6.2 kiloohms.
Yes, that I did not mean to put negative 12 volts. That's supposed to be positive. I'm like, my brain is one step ahead of me. If I didn't draw this as a negative, would you still say negative 12 over 6.3 kiloohms?
It's just the current's flowing
No,
down, so it should be positive.
I would say because the current is leaving the negative.
Yeah, that's
Passive sign convention.
yeah. So here's one way to think about it, right? First, I'm gonna get rid of this resistor. It's being shorted, right? So this is the circuit that we're working with, and we only have one battery, right? The 12-volt battery. And so conventionally, current is said to be leaving the positive terminal of batteries unless there's another battery that's sort of acting against it. Like if that was 100 volts, then this current could hypothetically be going like that, right? But the point is that there's only one battery in the circuit. So that means the current is going like this. And so let's try to look at that using KVL, right? This is obviously a very simple KVL. If we were to do a KVL here, it would be 12 volts. And remember, IL is going through this resistor like that. So we have plus, minus. And so it's going to be plus IL of 0 times 6.3 kiloohms equals 0. So if we were to solve for IL here, we would get negative 12 volts over 6.3 kiloohms. So the polarity of the battery here tells us that positive current should be flowing out of the positive terminal because it's the only battery in the circuit. And by convention, that's how currents flow out of batteries. That's just something you have to be like careful with. I don't know if there's probably a better way to explain it. I can't think of a better way other than just writing out a KVL that like definitively shows it. But that's essentially what's going on. If the battery was flipped, then you can say it's positive 12 over 6.3. So that's going to be negative 1.904 milliamps.
So we did like KVL, so the current's going inside the positive, out the negative, and then it enters the positive again because it's convention.
Yeah, so when we're doing, right, because this current is defined to be going, IL0 is defined to be going into the positive terminal of the battery, but that doesn't affect the KVL for the battery, right? When we go around in a circle, we still hit the positive terminal first, so that's why we put positive 12 volts. The current does, however, affect the polarity of this resistor. It tells us that plus is on the left and minus is on the right. So that's why we put plus I times 6.3. So yeah, the current direction doesn't affect battery sign for KVLs specifically.
Yeah. So it's just convention basically.
Yeah. Okay. That's step 1. And that is our circuit for t less than 0. Now, we're going to flip the switch. And we're solving for IL of infinity. So I'm going to go ahead and short out this inductor. Because there's nothing weird going on. We don't have any voltage sources in parallel with it. So we can just short it out. Right, and then this is the current we are solving for. That's 3.3K, 10K, 2.2K, 6.3K, 12 volts, plus minus 4.9K times IX. 7 milliamps. Okay. So, first things first. Let's simplify the circuit a little bit. And we're going to do that by getting rid of these two middle branch resistors because they are being shorted out. All right. Now, here's how I want to walk this through. I feel like this is probably the easiest way to think about this circuit. And hopefully this makes sense. So first thing I'm going to do is I'm going to set my grounds to be right there. Right? That's the first thing I'm going to do. Next thing I'm going to do is I'm going to write out a KCL. I'm going to call this current I1. And we know this current is 7 milliamps. So if we were to do a KCL, that KCL would be I1 is equal to IL of infinity plus 7 milliamps. And remember, we're solving for IL of infinity, so I'm going to solve for it and say that it is I1 minus 7 milliamps. Everyone still with me? Make sense? Just writing a KCL, had to define a current. We're given 7 milliamps. We're solving for IL of infinity. Now, the reason I defined my ground there is because I want to look at the relationship of the voltage across this 6.3 kilo ohm resistor. First thing I want to do is ask, what is the value of the voltage of this red node? Negative 12 volts. Right? So what could we say I1 is? Exactly. Which is the exact same expression as we just had, negative 1.904 milliamps. And hey, yeah, let's go back to this other problem real quick, right? You can think of this the same way. If you made this yellow node your ground, right, then obviously this becomes negative 12. And so if you want to solve for this current going from left to right, it's just negative 12 over 6.3. Another way to think of it that gets you the same answer. So yeah, that's exactly what we're going to do here to solve for I1. And then we're going to plug that into our KCL. So IL of infinity is equal to negative 1.904 minus 7 milliamps, which gives us negative 8.904 milliamps. And that's our IL of infinity. Still following? Cool. Any questions? All right. Let's get to our second to last step. And that is solving for the time constant. And yeah, so let's do that. All right. So we're going to remove the inductor, replace it with terminals. And then we're going to be using test source method because we have a dependent source. And when you solve for R Thevenin with dependent sources, really test source is your best bet. So when doing test source, you have to deactivate all independent sources. So voltage sources become short circuits. Current sources become open circuits. So I'm going to short the voltage source on the left and open the current source on the right. And we leave dependent sources intact. All right, 6.3K. And we are going to replace the terminals with a test source and define a current exiting that test source. call it.
I don't know.
Hi, Rishi. What are you doing?
I was just in here and I saw this shit. So by here.
Oh, nice. Yeah, make yourself at home, man. We're doing some Circuits 2 review. How's it going, guys? What do you think?
Better than I was when I opened it.
Yeah, I'm happy to hear it. Alrighty. So let's solve for IT. This one's honestly not that bad, actually. It really isn't. So obviously we're gonna want to use nodal analysis, right? So let's define the bottom to be the ground here. And this top node is going to be 1 volt, right? Because we're dealing with a super node here. So that top node is going to be 1 volt. And so we could actually just do a giant KCL and solve for IT. And I'm gonna write that equation out real quick, and I want you to tell me if that makes sense.
I guess we can just ignore the dependent source.
We can. Because it's connected to an open circuit and does not affect anything in our equations, which interestingly enough means that this is one of those really weird cases where you can actually still use R equivalent even though there's a dependent source, because it does not impact the circuit. But
10 kilo ohms,
Hmm?
the 10 kilo ohm resistor.
Exactly, yeah, that 10 kilo ohm resistor is not relevant to us. So this whole branch is completely irrelevant to us, which means that yes, you can absolutely use R equivalent. So that's our equation. R Thevenin is equal to 1 volt over IT, which is 1.09 kilo ohms, right? And so tau is going to be L over R. RL is 7. So it's going to be 6.414 milliseconds. Oh, it's a numerical value. Yeah. 6.414 milliseconds.
Is that 7 over?
It's, yeah, 7 Henrys over 1.09 kilo ohms. So yeah, that's our time constant. Now we have everything we need to build our equation. IL of t is going to be IL of infinity, which is negative 8.9 milliamps, plus IL of 0 minus IL of infinity, which is negative 1.904 plus 8.904. So you get plus 7 milliamps e to the negative t over tau, which is 6.414 milliseconds. And that is for t greater than or equal to 0. What's up?
Could you find the resistance by R equivalent, like the equivalence method real quick?
Yeah.
I try to do it like that, it's not that good.
Yeah, of course. So remember, I got rid of the entire right-hand branch because it is connected to an open circuit and it is not relevant to us. So that's gone, and now we're working with these 2 terminals. And so we have 3 resistors that are in parallel, right? Do we see that? These resistors are in parallel with those two terminals. In fact, if we shift this 6.3 ohm resistor, which we can totally do, it becomes a little bit more geometrically apparent that these are all in parallel. So our equivalent is 2.2 plus 1 over 3.3, all of that to the power of -1. And that's in kilo ohms. And that's going to give you 1.09 kilo ohms. All right. So, yeah. Now we need to, the last step, find Vx. So we are going to redraw the circuits for one last time. We're going to redraw it for after the switch flips because it's asking for Vx at 5 milliseconds, which is after 0. Okay, now there's a bunch of ways we can go about doing this. We can do nodal analysis, which is kind of what we're going to be doing, but we're going to be doing a slightly, easier version of it. We're not going to need a system of equations and all that stuff. In fact, I'm only going to label the value for the 12 voltage source, the 6.3 kilo ohm resistor, and this inductor. IL of t. Okay, now let's define the voltage across this inductor. And remember, inductors and capacitors are passive components, the same as resistors. So current is entering the positive terminals of these components. So we found our IL of t to be going down, so consequently the positive terminal of the inductor is going to be at the top. Now, let's define this to, of course, be VL. Now, let's define our ground, let me take a step back a little bit. Here's what we're looking for. We're looking for Vx, right? The voltage across this resistor. Now, let's say we called our ground to be at the bottom. That means this node right here is negative 12 volts. What's up? This node right above our battery is negative 12 volts. And this node at the top is VL. So what would Vx here be in this case?
Negative 12 volts minus VL.
Exactly. Yep.
Thank you so much.
Of course. I am screen recording.
You are?
I am. I hope it's capturing audio even though I'm screen sharing. It should be though.
It should, yeah.
Yeah. Okay. So that's our equation. Now we just need to find VL and we can solve for Vx. Thankfully, finding VL is super easy. We found IL. So we can say that VL is simply just L times the derivative of IL. Yeah, so again, there's a bunch of different ways we could have gone about this. What I did is I chose our ground to be right here, which means that we can call this node to the left of Vx negative 12 volts, right? The same way we did for the other steps. And similarly, we can call the node above the inductor VL, right? So by taking the voltage difference for Vx, the positive side minus the negative side, we get negative 12 minus VL.
Okay, okay. Gotcha.
Yeah. So,
He just bought 5 oranges from the market.
Bro,
How much is it?
bro, go through it, dude. There's something, man.
if you
Dude,
want oranges, let me know. I can
Dad's not
get
taking the
back.
divorce well. Okay, all right. So, VL is going to be L, which is 7 henries, times the derivative of IL of t. Remember, the derivative of a constant is going to go to 0. This is going to remain the same, and all we need to do is use chain rule to find what we're going to multiply this by. So we take the derivative of the exponent in our exponential term. So it's just going to be negative 1 over 6.414
Okay, I understand.
milliseconds. Careful, milliseconds. Let me move this. All right, now that's going to be all multiplied by 7 milliamps e to the negative t over 6.414 milliseconds. All right. Key thing to note here is that the milliamps is going to cancel out with the milliseconds. So you don't have to worry too much about units. You just do 7 times 7 divided by 6.414 times negative 1, obviously, to get you negative 7.64 volts e to the negative t over 6.414 milliseconds. And that's for t greater than 0. That is our VL. So, Vx of t is just going to be negative 12 minus this expression. So negative 12 minus negative 7.64. So plus 7.64 e to the negative t over 6.414 milliseconds. That's all volts. And this describes Vx for t greater than 0. Last step is just going to be plugging in 0.5? Or no, just 5 milliseconds. 5 milliseconds. So I'm just going to do that in my calculator real quick. Negative 12 plus 7.64 times e to the negative 5 over 6.414. Oops. 6.414. Which gives us negative 8.5 volts. Which is correct.
Wow.
That's a nice number.
And that is problem 2. It's actually not that nice. I just rounded it to make it nice. All right.